You know Dex plus IBT, IBT.
It is x. Okay. F of x equals e to the 2x minus sine x. Find d2y dx squared. So you have to find the derivative not once but twice. So you get f prime of x equals 2 e to the 2x minus cosine x. Then you have to find it again. And you get 4 e to the 2x minus a minus or a positive sine x. Good? So A?
Yeah, I'm good with that. Isn't there some instances where you have to plug it back
That's
in?
when you're implicit.
Yes, that's implicit.
Okay, that's
A graph of g of x is given below on the interval 0 to 10. On which of the open intervals can g of x use the mean value theorem? So what does the mean value theorem have to have? It must be continuous. It must be differentiable. It's the mean value theorem. Yeah. But mean value theorem says that the slope of the secant equals the slope of the tangent at any given point if you have a closed interval that is continuous and differentiable on the open interval. So since we're talking about the open intervals, it needs to be continuous and differentiable on the interval. So from 0 to 3, is that continuous?
No.
Boom, cross it out. From 2 to 4, is that continuous? It's continuous but not differentiable. Boom, cross it out. 4 to 8.
Just continuity.
Boom, cross it out.
7 to 9.
7 to 9. Okay, number 3, let h be the function defined above where a is a constant. If h is continuous at x equals 0, what is the value of a? So we already know continuity. We know it's continuous. So if you plug in 0, I know that a, anything to the 0 power is, so e to the 0 became 1, so that becomes a plus 3 equals 5 minus, what's the cosine of 0? 1. So 5 minus 1 becomes, so you get a equals 4 minus 3. Okay, which is B. Number 4, a particle is moving up and down the y-axis rather on the interval 0, 5. The table below gives selected values of position, velocity, and acceleration. At what time is the particle speeding up?
1, B.
Perfect.
And it's not at 5 because it's 0.
Correct. Okay, the function h is continuous and differentiable, defined by h equals f of g of x, function composition, therefore chain rule. The graph of g of x is given below. If the derivative h prime of c is negative for all c values that are positive, which of the following could be the graph of f? So you need to figure out, okay, what is h prime of x? Well, it's f prime of g of x times g prime of x, right? Because it's the outside times the inside. Well, the graph of g is given below. What do you know about the derivative of that graph? So if that's g is always, exactly, g is always increasing. Therefore, g prime is always positive. And h prime needs to be negative. So the graph of f needs to be negative. Therefore, the graph of f needs to be decreasing, which is only option
C.
Perfect.
Couldn't I just look at that and say that's the only graph where whenever it's, like, it's literally the only one that's decreasing?
Yeah, I mean, but that's the logic. You had to reason to get there. I'm sort of going through like as if you forget all of that. So yeah, this is a big chunk of the AP test, Unit 5. Now I like sort of mixed parts of Unit 5 into what we've been reviewing. Because if you think about like tangent lines, that's part of Unit 5. But Unit 5 is the theorems. So that's why I think it becomes such a big chunk of the AP exam, because Unit 5 is MVT, IVT, EVT, increase, decrease. So these problems get incorporated in like every problem. So even though necessarily the question may not be particular to that, it's a part of it. So the intermediate value theorem, literally, like think about the intermediate, like elementary. Intermediate elementary is like between elementary school and like middle and high school. Like we don't have an intermediate building, but like a lot of schools do. It's that awkward age where you're like not a little kid, but you're not a teenager. So intermediate means it lives between them. So the intermediate value theorem says if you have a continuous function, then there lies a point guaranteed from the max to the min. So like the range of that function guarantees every point in between it. That's what IVT says. IVT, this is the big one, does not involve a derivative. So when you're looking at a problem, if there are mentions no derivative, you're thinking IVT. If it does not talk about a derivative, you think IVT.
And I want us to be continuous and on a closed interval, right?
Correct.
I think I feel like we did continuous.
Pretty much. All right, MVT guarantees if the function is differentiable. And what does differentiability imply? Continuity. So if it is differentiable on that open interval, therefore it is continuous, it guarantees that there exists a point at which the instantaneous rate of change equals the average rate of change. Slope of the tan equals slope of the secant. Slope of the tan equals slope of the secant. I rock equals A rock.
This was where you used your car driving.
Yes.
Example.
Yep. Because again, you can't average 35 miles an hour if you never hit 35 miles an hour. The average temperature for the weather outside today cannot be 55 degrees if at some point in the day it is not 55 degrees. Differentiability over an interval is super important to understand why this works, because if it's not differentiable, well, now that's, yeah, it's not guaranteed anymore. So sharp turns aren't differentiables. Tangents that have these overlapping like slopes just don't work that way. So does MVT apply to this example? From -5 to -1. And be very careful, the interval is not the entire graph. Does MVT apply?
No, Dr. Daniel.
No, because at x equals -3, which is in that interval, we have jumped discontinuity. Now, this time we are told G is differentiable. If we are told G is differentiable, then we know G is also continuous.
Is that also when they're meaning like twice differentiable?
Yes, that means it's continuous twice. And it means it's smooth and differentiable the first time. So basically, if it's twice differentiable, it means you can find G prime and G double prime. It guarantees both derivatives. So is there a number C
Yes.
in that interval such that the derivative equals -4? How do you find it? What 2 points are you going to pick? Because there are a whole lot of points.
-5 and -3.
Yeah.
You're just going to do the slope of the secant.
Yep.
Which is -4.
Because MVT justifies that the slope of the secant is equal to slope of the secant.
Yep.
So we need to prove that the slope of the secant is equal.
So if you pick the slope of the secant at those endpoints, you get -4. So since the slope of the secant is equal to -4, then that means that the slope of the tangent at some point has to also be -4. So yes. EVT.
Oh, this is the one I see.
Yes. So EVT has the word extrema in it. Extremas are max or mins. EVT says that if a function is continuous on an open interval, then it must have at least one max and at least one min on the closed interval.
Does that have to be differentiable?
No, because it is continuous. So EVT could have an extrema at a sharp corner, like an absolute value.
Okay.
So that would still create an absolute,
Min.
exactly, even though you can't find the derivative at that point. Because EVT says that when you find the derivative, the critical points come from where the derivative is equal to 0 or where it does not exist. Exactly. So that's what makes EVT a little bit different. That's why differentiability is not necessary with EVT. An absolute max or an absolute min are the point where the function is the greatest. So EVT guarantees an absolute. EVT guarantees an absolute max and an absolute min. Guaranteed. They can be in the middle of the graph or the endpoints.
This is where we have to check all of them, right?
Yes.
And is that separate than what we did yesterday on the packet when we were plugging those in?
No, for number 8, or no, wait, the packet, yes. Yeah. The packet was initial position. That was actually more integration. That was like initial, that was displacement. Because you were given like, it would be like saying, if this line represents like the X and Y axis, like the point of intersection, the particle started 2 units to the right of that line. But then the particle went 8 units backwards. So that's like being negative 6 units here. Because the initial position mattered. It's like where you park in a parking lot and then move.
This is really atomic. The total distance is the absolute value of the final right versus absolute value.
Total distance is the absolute values of each change in direction. So every time the particle is at rest and changes direction, you have to find the absolute value for each of those points.
Okay.
Yes. No, you're good. It's a fair question.
And then the reason we picked those other points was because it was on 0.
It's when the velocity is equal to 0. Yes. Because when the velocity is equal to 0, it has a potential possibility in change of direction. It doesn't have to, though, because you can think about driving a car. Your velocity is 0 in a car when you're at a red light.
Yeah, because you could like go like, because I was thinking of like a graph, it could hit the X.
Yeah.
But would you subtract those or add all those absolute values? You
Add them. Okay, let f be a function with the selected values given in the table above. Which of the following statements could be true? By the intermediate value theorem, there is a value c in the interval 0 to 3, such that f of c equals 2.
Yes. Wow.
We're not told that it's continuous.
Yeah, that's right.
Yeah.
We're not told any of this is continuous.
So then
We
you
can't do
should-
anything.
Correct.
You tried to trick us.
I did.
Like, if we're not told it's continuous, we can't do any theorem.
Correct. Oh, it's like lightly in the background. Okay, let's find an example, or let's find the absolute value, extrema, of h of x equals 2x cubed plus 3x squared minus 12x over the interval -3 to 3. So first thing you have to do is find the derivative. So h prime of x, which is equal to 6x squared plus 6x minus 12. Then you have to set the derivative equal to 0 to find your critical points. Me too. So then my critical points become,
-2 and 1.
yep, -2 and 1.
So you have to test the endpoints.
Yeah, -3, -2.
Perfect.
Wait, do you plug it back into the original?
Correct.
Let me just see which one has the highest, the lowest.
Yep. Oops.
Why are we taking the sides?
To see if it is an extrema. But that was like if we were going to go into like local min, local max. You don't have to. Ugh.
Can I go to the bathroom?
Yeah. You get big numbers. What'd you get?
F of 3 is the max, and F of 1 is the min.
Yep. Yep. Because when you plug them in, there we go. My pen was not working. You have h of -3, h of -2, h of 1, and h of 3. H of 1 is -7, h of 3 is 45, 20, and 9. So that makes this the absolute max, and this the absolute min.
But that's just the absolute within that interval.
Technically, because it's a cubic function, there is no absolute max and absolute min because the end behavior is in opposite directions. That's what's so...
It'd be local.
Exactly. They would be your... Well, the locals would be at -2 and 1. 3 and -3 would not be locals because they would just be numbers in the graph. Yeah. So only -2 and 1 are locals.
Alright, that's on this.
So the first derivative test allows us to find the locals. The first derivative test allows us to find the locals when an absolute is not guaranteed. Sometimes on the first derivative test, though, we do find the absolutes because graphs like a quartic or a quadratic have absolutes. You find them by finding where the first derivative equals 0 or fails to exist. Where a derivative is equal to 0 or fails to exist is what we refer to as a critical point. A critical point represents an extrema if we have a sign change. Critical point represents an extrema if you have a sign change around it. So it has to go from, the original has to go from increasing to decreasing or decreasing to increasing. And the only way that happens if it goes to like positive to negative or negative to positive. So let's do a gross example. You have x squared over x minus 1. Find its derivative.
Let's McBride. This is more.
A quotient rule.
I know. See, it's not funny when you do it to me. It's only funny when I do it to you.
Sorry. So our derivative is x squared minus 2x all over x minus 1 quantity squared. X squared minus 2x all over quantity x minus 1 squared.
Just Heidi ho, Heidi hi.
All right, so to find the critical points, you would set those equal to 0. See, last time I used this was when we were given it had like technology. So you would, what?
I have a feeling it's going to be 0, 1, and 2.
I know. But you would set, what you do is set the numerator equal to 0 and the denominator equal to 0. Because where the denominator equals 0 is where f prime of x does not exist. And where the numerator equals 0 is where f prime of x equals 0. So that's where your zeros and your DNEs come into play. The zeros and the DNEs give critical points. Critical points represent potential extrema. Not guaranteed, potential extrema. Now, think back to that original function. What do I know about the graph of that original function that we did not talk about, but we should know?
There's a horizontal tangent at x equals 0, or something equals.
Not a tangent, a vertical asymptote. Yes.
Isn't there
So
also
we-
a horizontal one or something?
0.
0?
There's a vertical, well, you said tangent, not asymptote.
Same.
Vertical asymptote at x equals 1. Because if you plug in 1, 23.
Have you, it's
Not
funny
clear.
that you don't have access to the clock.
I'm the one that probably needs it the most.
I don't know. It's back there by my printer.
Sorry.
Okay. Vertical asymptote at x equals 1, horizontal at y equals 0. But what does that tell me about x equals 1 as a critical point?
It's invalid.
It's not going to be an extrema. Exactly. It's kind of quote unquote invalid. It's going to actually end up being to an infinity
X
above or below. X cannot equal 1. It's not in my domain.
But it just says x equals 1.
Is a critical point. It's not a potential extrema.
positive and negative 1. They're just gonna hate it.
No.
Well,
No. Something squared is always positive.
Oh wait, can I write that down? Sorry, I was
Spaced out a little.
yeah. I always thought we were still talking about the last problem, which was
Oops.
So it's just 0 and 2.
Their potential extrema. We're going to eventually, in like a line or two, after I tell you the definition of an extrema, we're going to figure out what's are which. So a relative max is a point where the function changes from increase to decrease, making it a peak in the graph. A relative min is where a function changes from decrease to increase. So that means on the derivative, it goes from positive to negative for a max or negative to positive for a min.
Is this the second derivative test then?
This is still part of the first derivative test. We're going to,
That's the double.
Second derivative test
is concavity. Yeah. But there is a part of the second derivative test that says
You can prove
if the first one is a 0 and the second derivative is negative, then that 0 of the original is a maximum. And then it's if the first derivative is, I hate the, that's the,
You don't need to use the second derivative, right? Can't you just always prove it through the first derivative?
yeah, the only time it doesn't work is if you have a table. And like, let's say you don't have like,
An equation.
so what lesson again?
so if the first derivative is a 0 and the second derivative is negative, then you have a max.
Oh yeah, I remember.
And then if the first derivative is a 0 and the second derivative is positive, then you have a min. Because
I remember all that from that one.
it's the
test
opposite of what you think it should be.
of
Like,
that cubic function. Remember
Well,
that
yeah, and
cubic one was just a big trick.
Well, and there's sometimes you had to specifically prove it through the second derivative
Yeah.
test.
there's like 1 or 2 multiple choice questions that could pop up. All right. So, I told you I screenshotted from Khan Academy. That's Khan Academy for you. We're gonna do it the way we know how to do it. I should actually just delete that chart off the paper. So take your critical points. So it's 1.
Imagine how long it took if you actually did the whole thing. Like
Me.
Guys,
0,
I
1,
had
2.
it done halfway. You haven't done it since chapter what, 7?
I did the whole thing though.
I'm saying, but you hadn't done it before it took so long.
Oh, I had work. I did my work.
All right, so you have 0, 1, and 2 as your critical points. You need to plug in test points around them. So that's where this -1, the 0.5, the 1.5.
We had a whole bunch of chapters done from when we went in groups and those projects. We flew them out while everybody did the projects.
That still doesn't mean I still didn't do it.
You did. Okay.
Yes, I'm entirely grateful.
Internally.
So if you plug in -1, at the top is always going to be positive, so we only really care about the bottom. So, well, no, wait. Yeah, my top is x squared minus whatever. That's the original. You need your derivative when you plug in. So you're plugging into and I said it backwards. The bottom is always positive, sorry. Because it's x minus 1 squared, and then this is x squared minus 2x, I think.
We plug it into the derivative.
Correct. So all of those red points go into the derivative. So the bottom is always positive. So -1 is positive, but then you have 1 minus a -2, so that becomes a positive, or a positive. Therefore, this graph is increasing. Plug in a half. A half squared is a fourth. Fourth minus 1 is negative. So therefore negative, therefore decreasing, therefore 0 exactly. As a local max. We know this graph is now going to a negative asymptote because it's decreasing. So then if you were talking about the limit as x approaches 1 from the left is negative infinity. From the right, we plug in 1.5, that's also negative. So it's decreasing here too. Oh wait, just drew that backwards. What time did it ring, Corey? It's pretty close to our normal time. We don't get messed up because of QRT and being back to back. And it's only a 1 hour early release, not a 2.
We don't really lose that much.
No.
It'll be 39, right? No, it'll be before that because we had 2 minutes off of first period.
No, first period was the same.
Oh, okay, so just 2 minutes off of these 2 periods.
So it's 4 minutes off, so it's 39. Yeah.
Oh,
We asked you and you didn't answer.
Well, I was listening.
So this goes decreasing to increasing, therefore.
yes. Corey, you haven't said, I think we're done for a while.
Well, that's because I am not in the position to argue for anything because
He's done for the day. That's why he's not helping out unless he's just done.
I sat here.
He
and did
quit a
my-
long time ago.
Yeah.
I sat here and did my lit for 40 minutes. I'm not in any position.
Why'd you even put my stuff away? We still have more lecture.
I didn't even think about it. I meant to put this away and the calc just happened to end up
Mhm.
moving, so. It's one of the days right now. I haven't done this much work this early in the morning in years.
So concavity relates to the rate of change of a function's derivative.
This is my strong suit.
A function f is concave up, where the derivative f prime is increasing. I do not. This is equivalent to the derivative of f prime, where f double prime is positive.
Now, when we get to like velocity and stuff, now that's where it goes downhill. But this right here is my strong suit.
But velocity is just.
Any more tests, Dewey?
It's the language that gets the terminology. Oh, I gotta work.
work tonight too. Me and Ava did the extra work together.
I was like, they're not going. Because I can see the D's too.
You
No,
hate
I'm
any younger class.
fine with it.
All right, inflection points. Inflection points are points where the graph of a function changes concavity.
I know.
Inflection points are found in a way similar to how we find extremas. However, you're looking for the sign changes on the second derivative.
Correct. So I knew that.
You want to come teach it?
No,
Yeah, please do, Corey.
I could probably do
Actually, I think
this
I can.
part.
So the second derivative test, much like the first, says find the second derivative, find all the candidates, which are the zeros and
This
DNEs,
is this acceleration now we're looking at.
analyze them.
Corey, can't you just think of it as acceleration now?
You didn't take physics.
It's the terminology.
What, do you need help
Corey,
with
you
physics?
can't blame that on physics.
Yeah, because I took physics.
I never.
I
never
know
said
more about
it was
physics from
physics
this
part.
class
Than I did in physics.
Because I had no idea what any
I
Now,
never
to-
said
now,
it
to
was
be
physics
fair,
part. I just said it was the terminology.
I'm through
Wait,
3
can you
years
go
of
back a
him,
second?
so I
I
learned
gotta
more
fill
over
something
there,
in.
but I mean,
What?
yeah.
Hey, 3 years.
You know, hold on.
You only had me.
3 years.
Let me just tell you
Took
something.
years, but what did you guys do?
Alex was gone, and I tried to do this, and I couldn't because Mannion actually made me do problems today with him. But he didn't do them. He said,
Terrible.
Wow, you mean a teacher actually taught?
You define this remaining teaching like kind of how me and Des would say, well, we're learning chemistry.
he
At
said,
least we learned some chemistry.
he
You guys do
made
this
me
one
do
now.
the problems, which still quite bad at because I gotta do them now, but like,
Sign test, sign chart. Was it you? Because you thought I was talking about the actual sign.
Yes,
You don't
and
like
you were
when I say
saying
that.
positive and negative. I like when you say, you say sign chart, I'm looking at the sign chart.
So that's what this is. That's this unit. This unit is the sign chart test. However, the sign chart is not a valid justification on the AP exam. You must put it into words,
Increasing or decreasing. I know.
or positive and negative.
Sign chart,
And you need to make sure you need to make sure you label the what? The function.
Yes.
right now we're on
Function.
right now we're on
I'm still mad
derivatives.
about
I know.
Right now we're on derivatives and doing X of t, A of t, B of t, that sort of stuff. But we're dealing with it with inverse